Hello, everyone, and welcome to the Future of the Data Center Roundtable. As we've seen from our presentations throughout the day, across global network infrastructure, the amount of data created is rising at an exponential rate. Transporting, processing, and securing all this data is driving big changes. From the core data centers to the edge of the network to the IoT devices and devices themselves. AI is being added everywhere. And as we all know, the technologies developed for the data center ultimately proliferate across all the verticals. So the future of the data center has big implications for the future of computing writ large. I'm Tim Messagy, and I'm joined by my panel of technology experts from across Rambus to discuss the future of the data center. My panelists are John Ebley, VP of Product Marketing for Memory Interface Chips, Matt Jones, VP of Strategic Marketing for Rambus, Mark Orthodoxou, who's VP of Strategic Marketing for Interconnect SoCs, Niraj Paliwal, General Manager of Security IP, and Steve Wu, Rambus Fellow and Distinguished Inventor. Steve, let's kick off with you and share with everybody your view of how this exponential rise in data is going to shape the evolution of the data center.
Yeah, Tim, that's a good way to start here. There's a lot of really interesting things that are going on, and it's really all a consequence of this exponential rise in the world's digital data. I'm going to touch on a few of them here, and then maybe we can kind of expand on them as we go on. I mean, first and foremost, when you have this much data and it's growing, you need some place to put it all, and that's really putting pressure on the memory industry to provide higher capacity to store this data. And once you've got the data, you need higher bandwidths to move that data back and forth between the memory and the processing elements. And then even beyond the processing and memory, you need faster interconnects so that you can move that data back and forth between different processors in the system. So that whole rise in the amount of data and the need to move it more quickly and efficiently is really generating a lot of new technologies and new solutions to help us do these things better. Some examples of that are right now, we're seeing a transition in the industry to the next main memory standard from DDR4 to DDR5. DDR5 is great. It gives you more capacity, it gives you better bandwidth, and it gives you better power efficiency as well. All things are very, very important as we move forward and continue to try and provide better computing solutions. And then in the links between our chips and our subsystems, PCI Express 5 is actually coming out. And so again, it's a leap in performance as we try and connect our systems and move the data, back and forth between things like cards and other processors in the system.
Right.
And then finally, there's another really great technology that's coming out that we'll be seeing here pretty soon called the Compute Express Link, or CXL. And what that new link offers is some very compelling things that will make computing in the data center much better. There are things like memory coherency and fast speeds that are actually built on and leverage industry standards like PCI Express Gen 5. And what it does is it really allows, as our data centers become more heterogeneous, it allows different things like CPUs and GPUs and accelerators and NICs and things like that to communicate better and to share memory as well. And so those are kind of the building blocks that we're starting to see that are emerging. In terms of things that are going to be built upon those building blocks and other trends, we're definitely seeing that the data itself and the insights that you can gather from that data are becoming more valuable. So security is rising in importance. And then, kind of at the chip level, what we're seeing is that, we've for many years, had the luxury of having something like Moore's Law that's always bought us more transistors and more capacity and more performance as well. But Moore's Law is slowing, and some of the things like power scaling kind of stopped in the early 2000s. And so the answer there was, instead of having more general processing architectures, was to go to a more purpose-built silicon. So one great example of that is the AI market, where we see people building specialized solutions, not so general, but that allow us to continue on these historic rates of improvement by having more targeted silicon. And that's really a trend we're expecting to continue to see going forward at the chip level. And then beyond the chip level, when you kind of assemble these things into a data center, what we're starting to see there is we're seeing some changes where, we're all used to this kind of mobile computing paradigm where we've got these endpoints like phones. They gather a bunch of data and send it into the cloud. I think people are realizing that's no longer the most efficient way to do things, both from a performance and power standpoint. And it's in many cases, the volume of data makes it hard to move it all to a remote data center. So we're starting to see some of that processing move out now towards the edge and towards the endpoints themselves. And one great example of that is AI inferencing, where people are really trying to push that more towards, where the data itself is being generated. Right. So there's going to be a trend of kind of moving some of the compute out of the centralized data centers as well. And then finally, kind of the last thing that I think is really kind of interesting is a little bit further out, is this move towards disaggregation and composability. So today, the way people, think about building servers is they have some amount of fixed resources that they put in a box, and then that's kind of what you have available to you when you work on a task. And it's no longer really the case that one size fits all. It's hard to match the resources you need, and the workloads are getting bigger and bigger, so it's harder to kind of put everything in one box to begin with. And so there's a move towards saying, well, maybe what we really ought to do is take our major resources like memory and compute and storage, put them into their own pools. And then when a job comes in, I kind of grab however many resources I need out of each pool and provision it until that job is done. And when I'm done with them, I put them back in the pools and they can be used for a future job. And so that kind of move towards disaggregation and composability is another, kind of important goal for the industry to improve performance and efficiency. And CXL is going to be, a key enabler and play a really big role in that as well. Yeah, it's something that Mark can talk a lot more about. I mean, he's really an expert in this area.
Well, why don't we hand off there, Mark? Would you mind sharing some thoughts about CXL?
Yeah. Thanks, Tim, and thanks, Steve, for the kind words. This is a super exciting time. I mean, CXL is it's arguably the biggest disruption in the data center since the introduction of NVMe flash storage. For the first time, there will be a ubiquitous open standard for the low latency coherent memory transaction ecosystem. The fact that CXL also operates over PCIe Gen 5 or PCIe electricals in general, because obviously there's going to be further generations after what's already been standardized. I mean, that's just going to make it more ubiquitous and more widely adopted. So when you look at it, though, it's going to happen in phases, right? It's not going to all happen all at once as all transitions, right? Initially, we certainly would expect that there will be more memory expansion through type 3 memory modules that will be directly connected to CPUs, GPUs, other compute elements. And those will be mostly for just pure memory expansion, capacity, bandwidth, more so than you can really achieve with native DRAM channels alone. But actually, those initial deployments using memory modules, they do more than just more capacity and more bandwidth to the CPU. They also introduce other elements that I think a lot of people don't appreciate. Mm-hmm. For one, this is the first time ever with the introduction of CXL that we'll have the opportunity to actually plug in an N-1 generation or an older generation of DRAM into a CPU that otherwise can only support, for example, DDR5. Imagine a DDR5 CPU that now uses DDR4 memory. And there's lots of reasons that might be desirable. For example, cost in applications where the performance is not required. Also, storage class memory now has a new vehicle for adoption. You don't need a proprietary interface. You don't need complex BIOS changes to enable it. So now we have a vehicle for SCM or storage class memory to find places in the ecosystem. There's also going to be opportunities for performance tuning or customization. A lot of existing implementations using off-the-shelf components are a little bit bound in what kind of tuning they can allow for. Now we have a much wider ecosystem of custom solutions and tuned solutions, which are going to be very important for the cloud service providers that have very unique workload dynamics that need to be addressed. And very importantly, finally, in this kind of first phase of deployment, we're going to see this, I think, this this benefit that the whole ecosystem will realize that will start to bring solution costs down. And the reason for that is because CPUs, GPUs, DPUs that take advantage of CXL attached memory, they have the option to provide more memory to their compute elements with while using fewer pins, right? So that's going to bring the die sizes, the package sizes down. So that's the first phase. And then the second phase, you know, what we would expect to see, I think, is more CXL attached memory moving out of the server into an appliance elsewhere in the rack, but nearby the server. That's often referred to as memory pooling. And in these types of architectures, the goal is really less about necessarily strictly adding more capacity or bandwidth to each compute element, but it's really about providing less memory stranding in a larger compute environment. So therefore, you can get to a dynamic where the service level agreements can be satisfied by the cloud service providers that are using it, for example, without having to over provision an individual server with as much memory as is required to handle the peak performance. You can actually dynamically allocate from server to server or CPU to CPU. We're also going to see, I think, eventually a movement towards near memory compute. The notion that you can actually take purposeful compute, often, you know, vector processing, and stick it closer to the memory. And the goal of that is to reduce a movement of data around the system. And that really just allows you to use expensive compute resources more efficiently. But I think finally, and, you know, Steve mentioned this a second ago, really the euphoria, as it were, is the fully composable rack level solution. And CXL, I would say, is the first open standard that allows for the composability or the disaggregation of not only compute and storage and networking. PCIe had done a pretty good job of that, at least at a moderate scale in its most recent incarnations. But with CXL, we also add memory to the disaggregation of the composability story. So we're going to see, I think, low latency fabric, sometimes quite large, that'll provide for a new level of scalable resource pooling, sharing, and clustering.
Wow. Okay. So lots of flexibility, lots of scalability. For folks who are not as familiar with CXL, Mark, you talked about type 3 device. Could you just explain for folks, what are the types? What is type when it comes to the devices?
Yeah, no, that's a great question. And it's a good point. It starts to become part of the vernacular and you forget. So CXL uses the language of hosts, meaning CPUs primarily, but can also be a GPU or any other PU, and devices, which are things that are attached to the hosts. And there's 3 types that are defined by CXL. There's type 1. Type 1 is really a processing device that has a coherent cache, but there's no direct attached host managed memory. So an example of that could be like a SmartNIC. Okay. Type 2 is really a processing device that has both the coherent cache and some locally attached memory that can be host managed as well. And a great example of that is an AI accelerator. Type 3 devices are really only presenting host managed memory to the compute complex. And so that is an example of the memory expansion devices and even the memory pooling devices that I mentioned a second ago. It's also important to note that CXL defines a few different protocols. There's CXL.io, CXL.mem, and CXL.cache, and which combination of those is being used is also dependent on the type. So a type 3 device would use a CXL.io and a CXL.mem protocol, by example.
Okay, that's very helpful. Thank you. And Niraj, as we, Steve and Mark articulated the desire to move to these disaggregated and composable architectures. But, and those are good. They have many benefits, but they also have implications for security. Could you talk about that?
Yeah, thanks, Tim. So Steve and Mark talked about data center interconnect disruption and CXL-derived benefits of disaggregation. But if you look from security perspective, as you separate the components of server architecture into pools, for a crypto architect, that increases the attack surface, which bad actors can attempt to exploit. So understanding this, CXL is really specified with a security by design approach. And it is secured via IDE, integrity and data encryption spec, which provides confidentiality, integrity, and replay protection. From security perspective, to meet the high-speed data rate requirements of CXL without introducing additional latency, IDE needs to be implemented in hardware level secure protocol engines. And they need to be instantiated in CXL chips. To draw a simple parallel, right? If you look back 8 years ago, you could do ML-specific algorithms on a CPU, but then you ended up getting in a situation where you need to have AI hardware accelerator chips. In a similar way, when we are looking at high-speed data rates and we have the bottlenecks related to latency, the security needs to be implemented with hardware acceleration of math in RTL level. So that's what it comes down to. And in addition to protecting the data, there's also a need to protect CXL-enabled chips and systems from tampering and cyber attacks, like any device that has valuable data. So, and we manage that by implementing hardware root of trust on the CXL chip, which will provide the basis for security and support all the requirements for applications like secure boot and secure firmware download. So that's how we look at this disruption in the data center and how we can enable security by design.
Great. So we could take advantage of the benefits of CXL, but still maintain the security levels that we have come to expect for the data center.
Absolutely.
You know, thank you, Neeraj. I want to go back to one of the things that Mark talked about, and that was, I think, a really brilliant decision by the consortium to adopt the PCI Express standard for the physical interface for CXL, because that just leverages this really ubiquitous technology, which is PCI Express. And Matt, I want to turn to you and ask, where are we with PCI Express? How is the PCI Express standard evolving?
Yeah, thanks, Tim. You know, and you and Mark both use the term ubiquitous. I think the other term, you know, we continue to use for PCI Express is, you know, long-lived or foundational.
Right.
It's become a bit overshadowed with some more exciting things. But I think the key thing is Mark talked about two revolutions in the data center, one in storage with NVMe and one coming for memory with CXL, both built on the backs of the electricals for PCIe and leveraging that ubiquity. So in and of itself, PCI Express continues to evolve dramatically to move data around both within servers and between servers within the data center, as Steve talked about, as an interconnect. And we see that, you know, with the rapid pace of evolution, not only in compute power, continuing on with that growth, but with the specialized compute that Steve talks about, the distribution and heterogeneity of computing, moving that data around more quickly. So the evolution continues to grow and evolve here. You know, as we talk about the data center, you look at something like PCIe 4.0 with you know, 16 gigatransfers per second. You know, that got you to about 64, or not about, to 64 gigabytes per second of bandwidth, which fell short of supporting 100 gig links. PCIe 5 brings that to the table while enabling the CXL interconnect for 2.0 coming shortly at the 32 gigatransfers rate. And we're going to continue to see that grow, not only to support the gigabit Ethernet links, but chip-to-chip connectivity, and to provide that foundation again for future generations of interconnect CXL. And, you know, who knows what's yet to be built upon PCIe, Tim.
And, you know, Matt, NRZ has been our friend and got us up to 32, but 64, to get to 64 gigatransfers per second, PCI 6 seems a pretty dramatic changes.
Yeah, Tim, you know, certainly, you know, we saw this when we moved in the PCIe world from 2.0 to 3.0, changing the encoding standard from 8B, 10B, to really create that efficiency to move from to double the data rate without by changing the encoding standard. The jump from PCIe 5 to 6 will be as big of a leap in a different sense. We do move, as you talk about, in terms of the signaling from NRZ to PAM4, pulse amplitude modulation with 4 levels, meaning that for each clock cycle, there are 2 bits instead of 1. And with that comes a good deal of other changes to support that advanced signaling rate. Specifically, it brings with it a higher bit error rate, which forced the standards body to, adopt forward error correction, and ensure that the standard was sufficiently lightweight and didn't introduce more latency. So lots of work done there. And then, PCIe had been known up until and through Gen 5 for, variable packet lengths or TLP lengths. In order to perform this error correction, necessarily brought into play fixed payload sizes, and the notion of flow control units or FLIT mode in PCIe. So, stemming from this, forklift upgrade in signaling, a number of things have evolved in the standard to support the doubling of that data rate. This change should provide a significant foundation for PCIe 7 and potentially beyond. So, a big step forward in the standard here.
Yeah, absolutely. Absolutely. Speaking of big steps forward and big new standard changes, John, we've got the next chapter of main memory to discuss. Can you kind of tell us where we are with the DDR5 rollout?
DDR5 is here. Almost. I want to give a little background about the technology, and then I will more directly answer that very important question. So I think, the exponential rise of data and the need to derive insights and infer from that really has a big implication on servers and CPUs. Workloads are getting bigger, more complex. And what we've seen the CPU companies do, and I think the hyperscalers have been encouraging in this, are to get more cores per socket. So that's been really one of the mega trends in the server world, is this increase of core count. Now, when that happens, the bandwidth and the capacity serving that socket needs to scale up proportionally.
Right.
And so that's a big challenge for the industry. And DDR5 has really been designed to rise up and meet this challenge and to provide that bandwidth and capacity in a more efficient way than previous generations. DDR5 has launched at a top speed of 4,800 megatransfers per second for now. That's an exciting number because it's a full 50% higher than the DDR4 end of life, which was at 3,200. And some of those efficiencies and protocol and channel efficiency leads to even higher performance gains. Micron has published a study where they see about another 37% on top of that. So a full 87% performance increase per channel, when you jump from a DDR4 to a DDR5 memory system.
Right. That's big.
Yeah. So circling back to your question a little more seriously, client systems have launched. You can go out today, buy a system with an Alder Lake CPU, buy DDR5 memory, kind of for the client market. In the servers, we are seeing the ecosystem slowly ramp, and we do expect, or we all eagerly are anticipating some public announcements around servers being available. So they're definitely coming. Now, as far as where we are in the transition, our first generation RCD running at 4,800 megatransfers per second has been in production for over a year. We've shipped a lot of parts. We're seeing good success there. And we're already ramping our Gen 2 version of the RCD, which runs at the next major speed bin of 5,600 mega transfers per second. We announced the availability of that last October, and we're in production ramping now. So we were the first in the industry to hit that milestone, and we're kind of staying ahead of the pace. So the memory system is ready when the systems are ready.
Right. And speaking of announcements, congratulations. Yesterday, your team announced the SPD hub and temperature sensor ICs. So that's two more chips from Rambus. Great. You talked about earlier in your presentation how for DDR5 we're really making a more intelligent DIMM. All of the additional telemetry and sensing and smarts that we're building into it. Can you just talk to us about what did the SPD hub and the temperature sensor do on the DIMM?
Yeah, definitely. Thanks for recognizing our press
You're
release.
very welcome.
This is very exciting for us. At Rambus, we've been mostly focused on really the signal integrity line rate chips, but this is the first time that we're introducing chips that do some of those companion functions on the DIMM to make it smarter and more intelligent. And that's really kind of broadened out our portfolio and really providing a full chipset to our DIMM customers. So yeah, let's start off with the hub. That's really the management gateway to the DIMM, and it's a bit of a Swiss Army knife. It serves a number of different functions. It serves its traditional role as really the non-volatile memory for the DIMM that stores the configuration information. So it has a kilobit of JEDEC defined space, and then we provide an extra half a kilobit of vendor-specific space. Its second function is a bidirectional redriver for I3C traffic. So with DDR5 comes the introduction of the I3C bus as the system management bus. In DDR4, it was I2C,
right,
running about 1 megahertz. This runs 10 times faster. Having a faster bus is important because it allows you to pull things in the system faster, and it also allows you to do more complicated initial training that's needed to bring the system up enough so that you can have that in-band communication. So this redriver, what it does is it sort of protects or it hides the loads of the I3C target devices on the DIMM from the main bus, which allows for higher speeds of operation. And then finally, it has an integrated temperature sensor on it. These hubs are not only used on server DIMMs, but they're also used in JEDEC defined for client UDIMMs and SODIMMs. So that's the hub. Second product we introduced was the standalone temperature sensor. It's an I3C device with high accuracy. It can be sort of spatially located on the DIMM at either end so that you can get a total of 3 different temperature readings per DIMM in the system. And so this fine-grained sensing within the system allows the system itself to be smarter and make decisions real time. It can control fan speed and kind of balance noise and power versus airflow. It can choose to change the refresh rate of the DRAM to increase reliability or performance. If those don't give you enough kind of control to keep things under temperature, you can choose then to throttle bandwidth. So those are the 2 devices that we have announced, and they're available, and we're looking forward to continuing to support the ecosystem in DDR5.
Wonderful. And they're leading to a smarter DIMM. John,
Yes.
Can you talk about some of the other innovations in DDR5 that really are intended to extend, its lifetime as a main memory solution? Because as you mentioned, kind of the lift gets harder with each generation as we go to higher speeds and more signal integrity issues to kind of tackle, and more technical issues, across a broad spectrum to tackle.
Yeah, no, it's a great question, right? When you do one of these heavy lifts, you want to have a technology that can extend out for, I would say, 10 years.
Right.
I think where DDR5 probably started on the right foot is to really have that big vision of where we're going. So I think having an end of life target at 8,400, 8,800 megatransfers per second,
Okay.
starting off at 4,800, right off of the bat, you're getting the whole industry moving in a direction where you're almost tripling the bandwidth that you had at the end of DDR4. One of the obvious changes in the standard to support capacity is really expanding the addressing space. So DDR4 maximum single die density was 16 gigabits.
Okay.
That's been expanded to 64 gigabits for DDR5. So if you take a 2-rank by 4 module that has single die packages on it, you go from a 64 gigabyte module to a 256 gigabyte module. Now, in order to get these higher density devices, you need to make some changes for the DRAM. One of the big changes was the introduction of on-chip ECC.
Mm-hmm.
This should allow the DRAM manufacturers to continue to scale capacitor and bit size by going to smaller and smaller geometries, which in turn will drive cost per bit down, which is very important. The other change was increasing the burst length for each transaction from 8 cycles to 16 cycles of data. So that relaxes the row activate time of the device, and once again allows us to scale the bandwidth up. Now, by making that choice, that led to some other decisions that were made at the module level, because when you do a transaction, what you want to get is a cache line. And so when you go to a 16 cycle burst length, you get twice as much data from a given set of pins. So the DIMM is now a dual channel DIMM. In DDR4, it was one single 72-bit channel.
Right.
64 bits of data plus 8 bits of ECC. Now what we have is 2 independent threads of control, and each channel is 32 bits of data plus 8 bits of ECC. You couldn't get away with just 4 bits of ECC because then you couldn't achieve the single error correct dual error detect reliability standard that we want to keep. You need I think theoretically 6 bits, so we round it up to the next divisible by 4 number of 40.
Right, exactly.
And that gives people a couple extra bits to do interesting things with.
Great.
The other nice thing about having the dual channels is at the CPU level, you now have more parallel resources for distributing memory traffic, and that should lead to lower loaded latency and higher bus efficiency. So speaking of efficiency, the other important thing is making sure you're power efficient and can manage the thermals of the system. So the voltage was dropped from 1.2 to 1.1 volt, so we could scale and increase the milliwatt per gigabit per second. The CA signaling was changed to a more efficient PODL, or pseudo open drain logic signaling, which is the same as the data bits. And I mentioned the hub and temperature sensor before, where we're looking to get more real-time information and be able to make intelligent decisions to stay within the thermal envelope. So I think, there's been a lot of thought put into the standard to allow it to extend for a long time. Going at these higher speeds at lower voltages is a challenge, but that's something that Rambus has been leading the way the last 30 years. So we look to continue doing that and helping our customers in the ecosystem.
Yeah, great. Fantastic, John. Thank you. Mark, as we move to an architecture where we will have our DIMMs for direct memory, and we'll have some memory form factors connected via CXL, will those look the same? Will they be different?
Yeah, that's also an excellent question, Tim. First of all, there's going to be lots of shapes and colors that will emerge over time. But I mentioned earlier the first phase of deployment, which was really about direct attachment of CXL memory, sort of inside a server unit. This is going to be required in time, even though the great strides that John mentioned on DDR5 over DDR4, you know, capacity, bandwidth is seeking to grow to match. There will be cases where this is required. And we really expect it to take two fundamental forms. The first one is an EDSFF compliant form factor. For those of you that are familiar with what's happened in the flash industry, a great deal of work happened within SNIA to standardize a form factor for flash drives that would be best suited to the media, the thermals, the amount that you wanted to place for capacity targets, et cetera. So that same module form factor is expected to be one of the popular form factors for CXL memory, in particular E3.S, but we'll also see over time, I'm sure, E1.S deployments as well. E3.S is more prominent, I think, in the early days, most likely because it allows for a footprint that allows you to populate a more interesting amount of memory. There's a lot of benefits of an EDSFF style form factor like an E3.S because, I mean, the infrastructure already exists, right? PCIe Gen 5 servers, as they come out in particular, the front of the servers for the most part will allow for a number of E3.S modules to plug right in. The backplane is already plumbed with PCIe lanes, which of course is the electrical foundation for CXL. And so that's likely to be one of the instantiations. The second category is, I think, going to take the form more of a PCIe chem style add-in card. And this is where worlds kind of collide and things get gray because those add-in cards, more likely than not, will actually have DIMM slots that will allow RDIMMs to be populated on them. This has a number of benefits as well. Here, if you want to get more bandwidth to a single group of memory, for example, you want to run 16 lanes of CXL 2.0, it can be actually quite a bit easier to access those interfaces on a CPU in a server by plugging such a card into the back of the server and not having to worry about routing that over the backplane with all the other storage and connectivity that has to happen to the front of the server. So that's one of the benefits. The second benefit, though, is quite notably, it allows for multi-memory vendor support. So if you have you're a big hyperscaler or a Fortune 500 company and you want some flexibility in which memory supplier you use on your memory expansion CXL modules, this gives you that flexibility, right? So I think a lot more will emerge. Those are two that stand out as sort of early likely form factors. Yeah. The one comment I'll make, though, an observation we can make just like talking through that is that beyond RDIMMs being directly attached to CPUs, which of course is not going to go away anytime soon, there's always going to be a desire to put memory close to the compute. There's actually a home for RDIMMs in the CXL ecosystem as well. So the two are highly complementary.
Yeah, it sure sounds like it. And Steve, one of the big catalysts for all of this change is our favorite workload, AI/ML. Can you talk about what's the latest going on in the AI/ML domain?
Sure. Yeah. It's again, this increase in the world's data is really driving a lot of these interesting changes. One of the things about the adoption of AI and ML, it's making it so pervasive, is with all this data in the world, AI and ML really are almost the only reasonable way to make sense of all of this data in a reasonable amount of time. And so when we think about AI and ML, there's kind of these two parts to it. One is training, and then one is inference. And so training is just that process of kind of teaching a neural network to do its job. And what we're seeing is that in order to be more accurate and to do more sophisticated tasks, what these AI engines, have to do is they have to become bigger, right? And they, have to have kind of more capability to differentiate between the noise and what it is they're really looking for. One of the astounding things about these AI models is that they're growing by about a factor of 10 per year. And so it used to be the case a couple of years ago that this, 1 trillion parameter mark was kind of this mythical ceiling, right, that everyone was really looking forward to. And we passed that last year. And, again, about 10x per year. And so now people talk about, getting to the next 100 or 1,000 times that size. None of these exponentials are going to go on forever, but this sure doesn't seem like it's stopping anytime soon. So the big things that we see now, at least from a training standpoint, are, you have to be able to tolerate and get to kind of higher capacities, and you got to get to much higher bandwidths. So the impact that we see on the memory systems is things like HBM3, they're really, and GDDR6, they're really being stressed in terms of their performance. Early on in the lifetime of those devices, people were already adopting the high-end data rates of those devices. It used to normally be you'd get some time before, the highest data rates were really demanded by the market. But, almost the moment these things are coming onto the market now, people want the high-end data rates and more. So that's one example of kind of how AI is really, helping to drive innovation on the memory side. We're also seeing, in the case of inference, what really matters a lot there is once you've kind of got this AI engine trained, you've got to get to an answer really quickly. And so some of the things we're seeing there are that, people are used to this cloud data center model, like I mentioned, where they might ship all their data to a cloud data center and have it analyzed there and then have the result come back. But these models are so big and the amount of data is getting to be so large that it's hard to ship it all over a great distance. And in fact, sometimes you need an answer very quickly. So you might have something that's a more real-time type application, something like, autonomous driving or something like that. And you really need to push that processing out closer to where the data is generated. And so, there, what we're seeing is kind of a change in the general architecture of the way processing's done. We're seeing a desire to move that processing more towards the endpoint. So there's just a couple of different ways that training and inference, in particular in AI, are affecting technology and system architectures.
Yeah, absolutely. John, trillion parameters. That's crazy town. What are some of the impacts on AI hardware?
Good question. Good question. I think general purpose CPUs, they want to be part of this game. That's the most exciting workload of the day. So they have been extending their instruction sets and their native data types to fit the machine learning algorithms better. Starting in the Cascade Lake generation, Intel started adding to their vector instructions and hardware, adding hardware for the convolutional neural nets. And they've been very public about what they're introducing into their next generation Xeon or Sapphire Rapids. They're introducing something called advanced matrix extensions. And this looks pretty exciting because they have the underlying hardware and instructions to deal with matrices. So they can efficiently store and manipulate them in two-dimensional register sets called tiles. And I think that's pretty neat. So I think the general purpose guys are going to want to be able to do the computation, and they're going to want to go up against the GPUs. And then so there's the CPUs, there's the GPUs, and then there are the specialized AI processors. Probably the best known one there is the Google Tensor Processing Unit, which has gone through 3 or 4 or 5 generations.
Right, exactly.
I've lost count, but so wherever you're doing this computation, the implementations and the algorithms require a tremendous amount of memory capacity and bandwidth to really keep these processing units fed. Mark earlier talked about type 2 devices. So I think, accelerators like this match CXL very well, right? So you can have a type 2 device that's this accelerator. It can have its own attached memory. That memory now is part of system space because it's cache coherent, and that's going to be much more efficient. The other advantage you have there is that type of memory, since CXL is agnostic, can be what is best for that particular accelerator. And so I think there's been a lot of great developments about developing memory that's specially tailored to those machine learning algorithms. And I think my friend Matt can provide much better details than I on what some of those specialized memories are.
Yeah, thanks, John. And sort of the term that comes to mind is horses for courses, and Steve touched on it, in some detail when we look at the AI workloads and the specific memories that that go along with them. If we take a look at training first, as Steve mentioned, the aptly named HBM or high bandwidth memory is the leading edge solution for these large training sets, and the latest version of it is HBM3, as Steve also talked about, and it's capable of delivering terabytes of memory bandwidth. And in the latest incarnation, if you have a 6-device architecture running with the fastest announced media at 6.4 gigabits per second, it gives you nearly 5 terabytes per second of bandwidth at a capacity of about 120 gigabytes. But as Steve mentioned, our Silicon IP team remains challenged to keep up with this 10x per year type of explosive data storage and usage. And the Rambus solution at time of announcement was a subsystem running at 8.4 gigabits per second, but we literally have the ecosystem both for core and specialized workload processing already talking to us about not only the next generation, but a couple of generations down the road. So that stress that Steve talked about of not only starting at the highest data rate, but looking beyond it already is very real in this AI training space. When we turn to inferencing, as Steve talked about, really the key here is moving that inference engine out and the computation out to the edge of the network or to the edge. What that brings with it is the use most commonly these days of graphics DDR, GDDR, and the GDDR6 standard. It brings the reliability necessary, the high bandwidth, and especially the price point as you move that commoditized memory and its performance out to the edge for things like ADAS-enabled cars, smart endpoints, and IoT. But again, here we're seeing a tremendous amount of stress put on for increased speed as the amount of data grows. Also as we move this memory and processing further towards the edge, certainly the security side of this becomes much more important. As Niraj talked about before, the attack surface as we disaggregate any of the processing and storage elements becomes much greater. So AI, not only in the processing world, but the interconnect and media and interface world is certainly bringing challenges. And our Silicon IP teams, both in security and in the memory interfaces, continue to be under that stress, as Steve talked about.
Right. And John brought up CXL and its connection to AI/ML. Mark, can you talk a little bit more and tie that one off on how CXL can help with AI/ML workloads?
Yeah, sure, Tim. I mean, I think John did a great job talking about how type 2 devices play a role. Maybe I'll focus on CXL memory attachment, how that plays a role. I mean, as Steve started off with, I mean, the AI and machine learning is a very memory intensive thing. The size of the models the training creates, the size of the data set used for the training. So broadly speaking, we can say that AI and machine learning, they increase the memory requirements of the data center. And as we've discussed, CXL is a great way to expand memory inside of a server. GPUs, for example, are increasingly used for AI compute. If you think of what a GPU needs to do, it basically needs to do very fast processing on very large data sets. So there's a combination of technology now available for it to take advantage of, obviously HBM, GDDR, and now CXL. So imagine a GPU with a modest amount of very high bandwidth HBM memory, but a very large amount of DRAM or some other media that's required to actually hold the model, for example, for inference purposes. Now let's take that multi-terabyte DRAM requirement and attach it via, 16 lanes of CXL 2.0. Well, realistically, that probably is going to require about 8 memory channels using native DDR5 to get the type of capacity that you'd actually want to get to that type of scale. So what we've just done is we've actually reduced the pin count required on that GPU to get at that capacity to less than 10% of what it would have been otherwise. So that's a very attractive thing for the the GPU ecosystem as they look at, if you've seen recent announcements from certain folks that are leaders in that space, the core count is just enormous. So if they can find a way to reduce the overall cost of the solution, the die size, et cetera, by reducing pins on the package, that's actually extremely attractive for them. The other factor is that this is a very compute intensive operation, as I mentioned, and the core count is growing. But if you need more cores than you can get on a single GPU to process the data, you basically have 2 options. You have to obviously duplicate that data, or at least a portion of the data, in a compute cluster, or you can provide a mechanism to share a larger set of data to process it in a coherent way. And CXL also provides mechanisms for that kind of memory sharing. So I think there's a couple of different things in the CXL attached memory space that are quite beneficial to the segment, beyond the introduction of cache coherent CXL type 2 devices as well.
Excellent. Niraj, we're down under, we got about 6 minutes left, and we've talked about some game-changing technologies today. I would be remiss if I didn't mention this one, and that's one big one looming on the horizon: quantum computing and its implications for security. Can you talk about that?
Absolutely, yes. It's just upon us now. So for cryptography, if you look at how the implementation is done and the math, we depend on the fact that digital computers will take a very, very long time, like hundreds of years, to solve hard mathematical problem at the foundation that's at the crypto algorithms, and which secures and protects the data. When we bring in quantum computers in this mix, there are 2 main algorithm categories on the cryptography: symmetric key cryptography, such as AES, where both the endpoints share the key ahead of time. Quantum computing doesn't really affect that as much. Okay. But for the public key cryptography, such as RSA, ECC, quantum computing really is affecting, and it's an existential event. For example, a fully developed quantum computer using a polynomial time algorithm for integer factorization, it'll be capable of cracking a pretty advanced, like 2048-bit RSA implementation in a matter of days, just a few days, with the quantum cryptography, compared to hundreds of years. So many of these secure applications depend on scalability of the PKE, public key cryptography. So this is an extremely serious issue as quantum computers become real in the next few years.
And NIST just made some important announcement relative to PQC and algorithms for the post-quantum era. Can you talk about that?
Yes. So if you are following crypto news, this was most hotly anticipated and highly, we were all waiting for this to come out. NIST has been sponsoring a competition since 2016 to kind of find, evaluate, and standardize crypto algorithms that will stand up to the challenges posed by quantum computers. And earlier this month, they had selected 4 algorithms for this standardization. 1 for key encapsulation and 3 for digital signatures. So if you really look at what they are, the key encapsulation one is NIST has chosen one algorithm family, and we call it Kyber. It's based on integer lattices and MLWE, module learning with errors. Compared to other candidates that were there for key encapsulation, this one convinced NIST that it has relatively good all-around performance, and a lot of security analysis has happened already. So that's Crystal's Kyber. That's the key encapsulation mechanism. For signatures, there are three different algorithms: Crystal Dilithium, Falcon, and Sphinx Plus. Now, being at the forefront of cryptography, our group had already anticipated that crystals would be a prime candidate. So we are already working with Kyber and Dilithium. We anticipated these things about 6 months ahead, and we're really glad we were spot on for this one. And kind of really excited to share here in this forum that hardware implementation, we would be the first one in the industry for our data center customers.
Wonderful.
And looking forward to rolling that out very soon. Last week, we rolled out a white paper really listing out all these things.
Excellent, excellent. Well, taking a look at the clock, gentlemen, we've only got a couple of minutes, so I want to thank all of you. These have been fantastic insights about the future of the data center. And to our audience, thank you all for joining us for this final session of RDS 2022. All the presentations that we've done today, they'll be available to you on demand. And if you have any follow-up questions for any of the presenters or any of our panelists here, you can use the Ask a Question links. Those will still all be live on the portal, or you can visit us at any time at rambus.com. If you've got a couple of extra minutes, if I could ask a favor, please fill out the event survey. We'd really appreciate your feedback, especially on topics for next year, so we can make this event even better in the future. I want to thank you all for joining us for RDS 2022, and have a great day.